Hello all, welcome to another video of statistics. Today I am going to discuss about ANOVA, which is analysis of variance. Now if you are a student of science, or social science or medical science or any other engineering background, or you are doing research on these topics, you are probably aware of this fact, or either you are an expert of this field or at least you are aware of the term ANOVA. So this video is for the beginner who are having doubts on ANOVA. What I'm going to do, I'm going to explain the every term of ANOVA from the scratch, and I'm going to explain and as well as implement things in R. Now ANOVA is a buzzword in the scientific field, and this curve is showing some trend of the research papers having used ANOVA tools for their research in last 10 years. So you can easily see that the use of ANOVA is growing in day by day, and it is not only in a single or two field, it is in various fields, right from the medical science, biological science, psychology and cognitive science, engineering, educations, and some social sciences like educations, human society, some art science, economics, history and archaeology as well, law and legal studies. So it is actually covering, encompassing various domain of science, social science, and and history, geology, etc. So you can sense the importance of this topic ANOVA. This is not new, but this is highly used in scientific and social communities. So today's agenda is we are going to look after obviously the ANOVA test, different types of ANOVA, and how to implement this. For that you need app test, practical example and implementation in R, and then I'm going to discuss about some differences between ANOVA and t-test. So if you go through the last few videos of mine, from about hypothesis testing, which you can find by clicking here in the I button. Now if you go through that playlist, we were actually concerned with the comparing or the means of two normal distributions using sample t-test, or for some independent samples. Now two distributions mean two groups, two sets of samples. Now what if I have to compare means of more than two distribution, more than two groups, and there your two sample t-test is not coming to any help, and ANOVA is actually here, will come to your rescue. Now an ANOVA test is a way to find out if survey or experiment results are significant. So it will answer whether your if you are conducting survey on different things, then if your result is significant enough or not, that you are going to get from ANOVA. In other words, they help you to figure out if you need to reject your hypothesis that you are conducting, that is your null hypothesis, and accept the alternate hypothesis. I have discussed about hypothesis testing, etc., in my last video, which you can go and find out clicking on the I button. Now for example, suppose you are a manufacturer in a company, and you are taking different processes for making a same light bulb, and after the end of the month you are worried, and you are trying to compare different processes, and you want to know whether one process is better than the other, or is there any best process among both those many processes that you have applied, and whether this comparison is significant or not. So this kind of question will be answered by ANOVA. So basically, when you are preparing some models from data, you are having some data, and in the data is nothing but dependent variables, and here in the ANOVA model you are finding some model, in any other model you are finding a model to explain the patterns in the data, right? And then your data model may not represent the whole data, and if your model is not most of the time it will not accommodate the whole data trend, then the component that is not accommodated by your model is represented as the error term, and your model plus the error is the actual data. here. So put all these things together, the basic question is, are there significant difference between the mean score obtained in different experimental conditions, and is there any difference, and are the difference significant? That you need to find out. And how do we do that? The mode here of the operation is comparing the variation in the dependent variable scores attribute to differences between the scores obtained in the experimental condition and the error term. So you need two things, that is your model and the error, that you need to find out here. So how do we do that? So the procedure starts with two main things, which is between group variance and within group variance. Here this is a pictorial representation of variation within a group and the between group. Here I have three groups, and the variation represented within a group is this within group variance, and the variation represented between these three groups individually obviously are between group variance. Now then you need to test whether these variances or variation are significant or not, and then a test you need to organize, which will be organized by F statistics, which will be tested by F statistics or F test. It is been introduced by Dr. Fisherman, and the size of the F statistics reflects the extent to which differences between conditions divert from the expected on the basis of chance, whether your variance is coming as a matter of chance or it is significant enough. F statistics is nothing but the ratio of between group variance and within group variance. So now if you have three groups like this, your group like 1, 2 and 3, and you want to test whether my groups are significantly different or not, then if your groups are significantly different, then obviously the variance between the group will be higher than the group variance within the group, obviously. And if your within group variance, either the total variance of the system is coming because of the within group variance, not because of the between group variance, then your F statistics will be lower, and you will say that my result or this group are not significantly different. You are not getting a significant result from that. So you can so in the first condition where your F statistics is higher, you can actually tell that I can reject the null hypothesis. Whereas in the second case, where the between group variance is lower than the within group variance and your F statistics is lower, you will say that I cannot reject my null hypothesis. So to compare the samples mean, it is graphically represented as this. If you are having a small f, your f value is falling something between here, and your p value is large, and when your p value is large, as you know from my last video, that if your p value is large, then you fail to reject the null hypothesis. And if your p value is significant, which is say something less than 0.05, then your f is actually falling here. That is because from the last slide, as you know, that between group variance is actually higher than this, and in that case your p value is very low, and you can reject the null hypothesis in order to accept your HA, which is the opposite to the null hypothesis. To put this in summation, that if the scores in the different conditions are influenced by experimental variable, then they vary between conditions, right? Your experimental variables are different, then obviously they will vary between the conditions. And if your variation of score within an experimental condition is there is a variation within an experiment condition, then that will be attributed to chance. Then if your variance of score between group has to greater than the variance of the scores experimental condition, else you cannot reject your null hypothesis. So to make this as a summation, what you need to do, I'll just put that in a step-by-step manner, is to implement your ANOVA. That your first step is to form the hypothesis. After you form your hypothesis, you need to follow the following steps in order to judge your hypothesis whether to accept or reject. So first you need to find the total sum of square in the system. How do you do that? I'll show you. your next step is find the variance. Variance is nothing but SST by the degree of freedom. Degree of freedom in the system is n minus 1, where n is the number of groups present in the system. And then you need to answer this question, that how much of the total variance which you have just find out is coming from the variation within the group, and how much of this is coming between the group variance. And how do you answer this question? You simply need to find out sum squared within, that will represent the within group variance, and then you need to find out the sum squared between SSB, which is the between group variation, and your SST will always be, that SST that you have find in the step 2 will always be SSB plus SSW. This is true always. And then finally you need to calculate your F statistics, which is nothing but SSB by n minus 1 by SSW by n into m minus 1. What is n? N is the number of groups, and m is the number of items in the groups. And you need to check if the observed F that you find out in the step 6 is greater than the cutoff F. How do you find out the cutoff F? Obviously you have a F test table where you find out the cutoff F by given the degree of freedom. Now if this is true, that your observed F is greater than the cutoff F, then you reject the null hypothesis, else you accept the null hypothesis. So this is how you implement ANOVA step by step. So here I will take a practical example and explain the step by step methods of ANOVA. And so here I have three groups, G1, G2, G3. Let it be three different foods are given to different samples, each having three people in the sample group G1, G2 and G3. And the question is that, is the mean population of taking food G1 is equal to the mean population of taking food G2 and G3. Mean population, which is represented by mu, is unknown. What we know is the sample mean. Population mean is unknown, and from the sample mean we have to derive the explanation about the population mean. That is the hypothesis we have, is whether the mu1 is equal to mu2 or equal to mu3. This is my null hypothesis, whereas my alternative hypothesis will be mu1, mu2 and mu3 are not equal. This is what we need to have. So in the first step we have the hypothesis H0 and HA, my null hypothesis that food habit does not make any difference, and contradictory to this is the alternate hypothesis, which is the food are making difference in their health. So first step, I have to find out what is my group mean R, that is, see, this is x1 bar, which is my group mean, and then it will be x2 bar, my group mean of the group G2, and then my group mean for the groups G3 will be x3 bar, and then finally I will find out x double bar, which is my grand mean. X1 bar I found out it is 85.33, x2 bar is 77.67, x3 is 97.33. So already you can see there is some difference between the group mean, but the question is again, what this is only sample mean. Is this sample mean is reflecting what is happening in the population mean or not? That is the hypothesis that we need to prove. Now let's see what is grand mean, which obviously will be x1 bar plus x2 bar by x3 bar by 3, which is 86.77. Step 2, I will find out the total sum of square, SST. Now how do we find out total sum of square? Here see, the 89 minus 86.77 square, that is the sum of square for this value. Similarly 84 minus this will be the sum of square for this value. For all the 9 values I will find out the sum of square, and total sum of square will be summation of that. In step 3 we find the variance, which is SST by the degree of freedom. Now what is degree of freedom? Degree of freedom is n minus 1, where n is the number of item in a sample. Why? Because in case of mean, if you know the two sample, so if you know two items in a sample, you can guess the third item, or you can evaluate the third item because you know the mean. So the degree of freedom in case of this will be n minus 1. So here see, I have 9 items in total. For the grand mean I have 9 items, and if I know 8 of them, I can guess the third, I can evaluate the last one. My degree of freedom is 8 here, 9 minus 1. So variance will be that is SST by degree of freedom, which is 136.5 and 2. Okay, so now the question is this: how much of this total variance come from the variation within the group, and between the, how much is coming from between the group? So that I need to answer. So okay, then in step 4 I need to calculate sum squared within SSW, which is, so sum squared within value. Now see, sum squared within will be like 89 minus 85.33, because 85.33 is the group mean for G1. Similarly 84 minus that, 83 minus that, and next for I have to find out for the group G2, which is 73 minus 77.67. For G3 it will start from 88 minus 97.33 up to 110 minus 97.33 whole square. So that will be 314 point this. Now in step 5 I need to find out sum squared between. Now sum squared between is the sample size. Sample size here is 3 into x1 bar minus x double bar's whole square. That is the difference between your sample mean minus the grand mean whole square. Similarly for n2 and 3, all of them will be 3. That is the sample size, and then you calculate all these things, it will be 589.19. This is sum squared between. So you get sum squared within is 314 and in sum squared between is 589.19, and you add them up and you will get the sum squared total, which is 1092.4. so this will be same, sum squared total is equal to sum squared between plus sum squared within. You just add them up and you will get this. And also the degree of freedom for sum squared total, you find it, see, mn minus 1, where m is the number of sample, m is the number of samples, that is number of groups, and n is the number in the number of item in each sample. So mn minus 1 is typically 3 into 3 minus 1, in this case will be 8, right? And sum squared between in each of the cases where n minus 1, which is 3 minus 1, plus for the sum squared within the degree of freedom will be n into m minus 1, which is 3 into 2, which is 6. So you just add them up. See, 6 plus 2 is 8, right? 9 minus 1 is also 8. So this as their degree of freedom will also be same. If we add the degree of freedom of SSB and SSW, we get the degree of freedom in case of SST. Okay, now you have found out these values, SSB and SSW. You can easily now answer this question, that how much of the total variance comes from SSB and how much comes from SSW. It typically is the ratio of SSB and SSW, right? So here F statistics need to be calculated in step 6, which is the Fisher statistics. It is the formula SSB by n minus 1 by SSW by n into m minus 1 are the degree of freedoms, right? So here 589.19 by 2 and 314 by 6 is close to 5.63. Okay, so you got the F statistics. Now in the final step you need to find out whether this F statistic that you have just find out, the observed F statistics, is greater than or less than the critical value for this much degree of freedom, right? And then you need to find out critical value. And how do you find the critical value? You can find out the critical value from a statistics table given the degree of freedoms, or you can take help from R as well. I will show you detail how to take help from R. The command is QF, and here this is the confidence that you need to put out. The confidence value that I have discussed in my earlier videos, which is 1 minus alpha. Here alpha is the critical value, and you would alpha maybe let's say 90%, 95%, like that. So how much confidence you have, that you need to put out here with the degree of freedom in the degree of freedom in 1 and degree of df1 and df2 are the degree of freedoms like 2 and 6 here that I have given. If you just put out this will be critical F 3.46 in R, you'll find out, and your observed F is 5.63, which is greater than the cutoff F. So you can reject the null hypothesis in order to accept your alternate hypothesis. So this is how it goes if you just calculate by hand. Okay, now I will take another example. In this example I will I will evaluate the statistics and all ANOVA tests using R. So here in this example I have three types of smoker: chain smoker, non-smoker, and passive smoker, and want to test a hypothesis that whether smoking causes lung cancer or not. And I have taken expression levels of a gene called Agar gene, which is a biomarker established for lung cancer, and with this expression level I can check whether this expression level is altered in three groups or not. So okay, so I have taken a significant level of 0.1, that is a confidence of 90%, and now I am to test how much is my p-value. So I'll go to R, and okay, so I have written a few line of code which I'll be give in the description section in this video. Okay, so I have taken these three groups of samples, which is chain smoker, non-smoker, and passive smoker, and then I will go to here. I will take this as combined column, which is which is a data frame object of CS, NS, and PS, and then if you just take this, you'll get the result here. Okay, so this is my CS, NS, and PS. Okay, so now I will stack them into a stack which is known as stacked column. Okay, so my stacked column will be like this. This is my stacked column, so it will contain all the 9 observations because I want to find out the group mean. So okay, so now let us find out the group mean, which is which I have taken as GM. That is the mean of the stack column. Now what is my group mean value is 4.04 here. You can see. Okay, now I'll find out the mx1, which is the mean of the CS. Okay, so the mean of the CS is 2.03. okay, and mx2, which is the mean of the CS, which is 4, and mx3, which is the mean of PS. Okay, so there you go, 6.1. now I need to find out the SST. As I know, SST is equal to the stacked column values square, right? This is sum of stacked column values minus the group mean square, right? This is my SST. So what is the value of SST? 30.26 here. Okay, and what is my degree of freedom? Degree of freedom is the length of the stack column values minus 1, right, which will be eventually 2, I think. So degree of freedom here is 3 into 3 by 3 into 3 minus 1, which is 8. Okay, so my variance will be SST by the degree of freedom, which is 3.78. so now I have to find out the sum squared within, right? Sum squared within is my CS minus mx1 whole square plus ns minus mx2 whole square plus ps minus mx3 whole square, right? This is my sum squared within, so 5.46. and similarly my sum squared between will be according to that formula, n1 into mx1 minus gm whole square, n1 into mx2 into minus all. I have taken n1 because in all these cases, because the value the number of items in all these group samples were same, so I have taken n1. If it is different, then I had to take n2, n3, etc. Now what is my SSB value? SSB value I have taken, see, n1 is not found because I have not run this line, so let me run this line first and then I will find out the SSB value, which is, see, it's 24.81. so if you just add them up, SSB plus SSW, you will get the value eventually, which is SST value, right? 30.26, which is the SST value. As I said, that SST will be equal to with SSB plus SSW, right? Now you need to find out the F, right? F statistics. So F statistics is SSB by the degree of freedom there, which is A3 minus 1, 2, and SSW will be n into m minus 1, right? N into m minus 1 will be 3 into 2, which is 6. So your F value here is, see, F value is 13.668, right? Now you need to check whether this F value is statistically significant or not. That is, you need to find out QF 0.9, 2, 6, which is this 3.46. Now you have to check your p value, right? In this, with this F, you need to check out your p value, and the degree of freedom is like 2 and 6. and you will check the p-value here is 0.005. so anything greater than anything less than 0.05 is a significant value in terms of p-value. You can check. So this is a significant p-value. Now we can conclude that I can reject my null hypothesis in order to accept my alternate hypothesis is this, that lung cancer is caused by smoking, right? So this is your alternate hypothesis that you have established. Now you may wonder that whether you have to write these many lines of codes in R in order to find ANOVA test every time. No, you do not need those many lines, because AOV is a function which will do it for you, right? You need to take this AOV, and within bracket you need to give values which is dependent on I and D. What you need to do is this, just run this line, which is AOV function with the data stack column, where use values dependent on indices I and D, and that will be done. And just to put the summary, in order to get the summary here, see your F value is 13.67, but you have got that F value by manually computing all these things, and your p value is 0.0058. so your result is significant enough in order to accept the alternate hypothesis. This is how you do in R. Now let's get back to our example. So I've done this example. Now the remaining part is that how many types of ANOVA are there. There are two types of ANOVA, which is obviously one-way and two-way ANOVA. In case of one-way ANOVA, we have only one independent variable with two levels, and in case of two-way ANOVA, it is named as two-way because it has two independent variables, and that can have multiple levels as well. Okay, so the example that we had taken where we had only one independent variable, so examples were like one-way ANOVA. Now what is an example of two-way ANOVA? Suppose we want to find out if there is an interaction between income and gender for anxiety level. So here anxiety level is a dependent variable on two independent variables, income and gender, so it will be a two-way ANOVA. Now two-way ANOVA, it can be with replication and without replication. What is replication? So replication means we have the same population or same sample set after and before and after some test. So this is without replication. So you have same sample before, and then you conduct a test and you take the data after the test. This is called without replication. And what is with replication? You have two samples, like suppose you are testing some drug effect on two samples in two different hospitals, and this is C1 and C2, and this is called with replication. In the end, what is the difference between t-test and ANOVA, or where you should apply t-test and where you should apply ANOVA? So if you have only one sample, then you can have one sample t-test, right? That we have seen in our earlier videos. But if you have two samples, and if they are dependent, then you need to have paired sample t-test, right? And if you have two samples but they are independent, then if they have equal variance, then you have independent sample t-test, right? All these go in within the t-test, right? If they are unequal, then you have independent sample t-test with approximation of degree of freedom. But if you have more than two samples, you are not going to have t-test, you are going to have ANOVA, right? As we had in our case, like H0, that is your null hypothesis. You have t number of groups of samples, then you have mu1 equal to mu2 up to mu t, right? This is your null hypothesis. Your alternate hypothesis will be unequal, right? Mu1 is not equal to mu2, not equal to mu3, like that. So that's all in this video. Thank you for watching, and please subscribe my channel.